Hi there, and welcome to the 6th class of the Archimedes Academy by IMSystems. The last class today and the next class, we're going to discuss the working principles of the Archimedes drive. But to really understand that, you first need to know how traction drives work, which we discussed in the last class, and how compound drives work, which we will discuss today. So, talking about compound drives, you can ask me, how do they work? But then I can only answer with, it depends. Because compound drives are a class of drives. They are planetary drives that in some way added an extra layer of moving parts that transmit torque. And the Nosferatu drive of the last class is actually already an example, because it has not one, but 2 layers of planetary drives. But it doesn't necessarily have to be an extra layer that's been added in the radial direction. You can, for example, also have 2 layers stacked on top of each other like this, with planet wheels that have one axis that moves at the same speed everywhere, but with different gears with different amount of teeth. And this particular example is called a Wolfrom drive. There are more compound types of drive, but today we will mostly discuss this. And if you look closely, you may have seen that next to this purple annulus, there's a second one that's yellow. You see it over here. And what happens is that the sun wheel on the input drives with the blue parts of the planet wheels that engage with the yellow annulus. But then they move to these smaller wheels that engage with the blue wheel. And to really explain how that works, I made a more schematic figure. So although the planet wheels, those are there, but we also have a lot of other components, and I'd like to call them, for convenience, by their function. And as we already discussed, you always need an input, an output, and a ground. And in the last picture, you didn't see an extra sun wheel, but sometimes to balance out the forces, you want it to be over here. And in that case, that component is idle. So the most common configuration of a Wolfrom drive you will see is that you have an input sun over here, and the planet wheels rotate around it, and then on the same side you have a ground annulus. And then on top of that, on the other side, you have the output annulus and this idle sun wheel. Just like with other planetary drives, you can mix these 4 functions and assign them to other components that affects the gear ratio. But for now, I also want to explain how you calculate the gear ratio in this very common configuration. So first, something you are already familiar with. When I showed the picture with how to calculate reduction ratios of planetary drives, I showed you the one where the planets are standing still or no function, that the sun was the input and the annulus the output. That led to this fraction, the teeth of the annulus divided by the teeth of the sun. But the teeth, if they need to mesh in every layer, they scale with diameter because they are the same size everywhere. So instead of teeth, you can also say diameter. And because of future calculations, I already want to make this step. So it's the same as saying, in this configuration, the diameter of the output annulus in purple divided by the diameter of this input sun. But now there's an extra interesting component because of the step that's made over here. And it works pretty much like a lever. We have the ground, and the ground is always the fulcrum. And the input, you can see it as a big lever pushing this output annulus away. And for a lever, you always calculate it by dividing this length over this length. So in this case, the diameter of the small planet times half the step size, because the step size happens over the whole diameter, and now it's only half of that. And you simply get the ratio of a Wolfram gear by multiplying this. So the diameter of the output annulus times small planet divided by the diameter of the input sun times this. And you can imagine that if you make a very small step size, like this is 30 teeth and this is 29 teeth. This is only a difference of 1/30th of the diameter. And if you go smaller and smaller, you can see that you create very, very high gear ratios. This can actually go higher than any other drive in existence. So now you know how the Wolfrom Drive works and how the ratio is calculated. Now let's take a look at the advantages and disadvantages, because we're going to use this in the next lecture. What the advantages and disadvantages are. You have that high ratio and high torque density because it is so compact. And well, it has a low efficiency because it's just so hard to make all those gears mesh perfectly. Or if you do that, it gets complex to manufacture and is very expensive. Thank you for listening to this lecture, because now finally in the next class, I can explain how the Archimedes drive works. And I'm very excited to do that, and I hope you are too. Thanks for watching, and if you have any questions, drop them down in the comments. Bye.